Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1934 marks a watershed moment in the history of nuclear physics, with Enrico Fermi's groundbreaking discovery of slow neutrons. This breakthrough, born from a blend of theoretical insight and ingenious experimentation, ushered in a new era of nuclear research and ultimately paved the way for controlled nuclear fission and the development of nuclear energy. Fermi's work extended far beyond a singular finding. It demonstrated the effectiveness of a systematic, empirically driven approach to nuclear investigation, an approach that influenced countless subsequent studies. Fermi, already a prominent figure in physics by the early 1930s, had made significant contributions to quantum statistics, leading to the development of Fermi-Dirac statistics, which governs the behavior of particles known as fermions. His work on beta decay, proposing the existence of a weak nuclear force, further solidified his position as a leading theoretical physicist. However, Fermi possessed a rare ability to bridge the gap between theory and experiment. This talent would prove crucial in his investigation of neutron-induced radioactivity. The discovery of the neutron by James Chadwick in 1932 opened up exciting new avenues for exploring the atomic nucleus. Unlike positively charged alpha particles, neutrons, possessing no electric charge, could penetrate the nucleus without experiencing repulsive Coulomb forces. This characteristic suggested that neutrons could be highly effective projectiles for inducing nuclear reactions. Initially, physicists focused on using fast neutrons, directly produced from nuclear reactions, to bombard various elements. Fermi, along with his team in Rome, including Emilio Sega, Edoardo Amaldi, Franco Rossetti, and Oscar D'Agostino, embarked on a systematic study of neutron-induced radioactivity. They irradiated a wide range of elements with neutrons produced by bombarding beryllium with alpha particles from a radon source. Their initial results were promising, as they observed that many elements became radioactive after neutron bombardment, emitting beta particles and transforming into different isotopes. This process, known as neutron activation, demonstrated the power of neutrons to induce nuclear transformations. A pivotal moment occurred when Fermi's group began experimenting with different materials placed between the neutron source and the target element. They observed that the intensity of induced radioactivity varied depending on the surrounding material. Initially, they attributed these variations to experimental error, dismissing them as insignificant fluctuations. However, Fermi's keen intuition led him to investigate these anomalies. On the morning of October 22, 1934, Fermi decided to replace a lead shield, which had previously shown a slight increase in activity, with a block of paraffin wax, a substance rich in hydrogen. To his astonishment, the radioactivity of the target element, silver, increased dramatically by factors of tens relative to using lead. This unexpected result triggered an intense period of investigation. Fermi quickly realized that the hydrogen in the paraffin wax was slowing down the neutrons. Fermi theorized that slow neutrons were more effective at inducing nuclear reactions than fast neutrons. He proposed that as neutrons slowed down, the probability of being captured by a nucleus increased. This inverse relationship between neutron velocity and capture probability, governed by the nuclear cross-section, became a cornerstone of neutron physics. The slower the neutron, the longer it spends in the vicinity of a nucleus, increasing the likelihood of interaction, leading to capture. To verify this hypothesis, Fermi's team conducted further experiments, replacing the paraffin wax with water, another hydrogen-rich substance. The results were similar. The induced radioactivity increased significantly with water as the moderator. These experiments provided strong evidence that slow neutrons were indeed much more effective at inducing nuclear reactions. Fermi's explanation for this phenomenon involved the concept of neutron resonance. Each nucleus possesses specific energy levels at which it is particularly likely to absorb a neutron. Fast neutrons, possessing a wide range of energies, have a lower probability of matching these resonance energies. Slow neutrons, on the other hand, having been slowed down through collisions with moderator atoms, have a higher probability of possessing the specific energy required for resonance capture. The discovery of slow neutrons had profound implications for nuclear physics. It immediately opened up new possibilities for studying nuclear reactions and for producing radioactive isotopes. Prior to Fermi's work, the production of radioisotopes was a laborious and inefficient process. Slow neutrons offered a relatively simple and efficient method for creating a wide range of radioactive elements. The implications of slow neutrons extended far beyond pure scientific research. The ability to produce radioisotopes in large quantities had significant applications in medicine, agriculture, and industry. Radioactive isotopes could be used as tracers to study biological processes, to diagnose and treat diseases, to monitor industrial processes. The most significant consequence of Fermi's discovery, however, lay in its contribution to the understanding of nuclear fission. In 1938, Otto Hahn and Fritz Strassmann, building upon Fermi's work with slow neutrons, discovered that bombarding uranium with neutrons resulted in the splitting of the uranium nucleus, releasing tremendous amounts of energy. This process, known as nuclear fission, was the key to unlocking nuclear energy. Fermi quickly recognized the potential of nuclear fission and played a crucial role in the development of the first nuclear reactor. In 1942, at the University of Chicago, Fermi led the team that achieved the first controlled self-sustaining nuclear chain reaction. This achievement marked a pivotal moment in human history, demonstrating the possibility of harnessing the power of the atom for energy production. Fermi's discovery of slow neutrons also had implications for the development of nuclear weapons. The chain reaction required to sustain nuclear fission is far more efficient when using slow neutrons. Thus, Fermi's contribution became a crucial to the Manhattan Project during the Second World War. It is important to note that the discovery of slow neutrons was not merely a serendipitous event. It was the result of a systematic and rigorous experimental program, guided by Fermi's deep understanding of physics and his exceptional ability to connect theory with experiment. Fermi's meticulous approach, characterized by careful observation, insightful analysis, relentless experimentation, set a new standard for nuclear risk. The initial reception of Fermi's work was, perhaps surprisingly, met with a degree of skepticism. The notion that slower neutrons could be more effective than faster neutrons ran counter to prevailing intuition. Some physicists initially questioned the validity of Fermi's experimental results, suggesting alternative explanations for the observed phenomena. The concept of neutron resonance, while theoretically sound, was difficult to verify experimentally at the time, adding to the initial uncertainty. However, as Fermi and his team continued to refine their experimental techniques and to provide further evidence supporting their hypothesis, the skepticism gradually subsided. Independent confirmation of Fermi's results from other laboratories around the world further solidified the acceptance of his discovery. The theoretical framework underpinning Fermi's explanation, based on neutron resonance and the inverse relationship between neutron velocity and capture probability, ultimately proved to be robust and consistent with subsequent experimental findings. The discovery of slow neutrons also prompted a re-evaluation of existing nuclear models. The liquid drop model of the nucleus, which had been dominant prior to Fermi's work, struggled to explain the enhanced effectiveness of slow neutrons. More sophisticated models, incorporating quantum mechanical effects and taking into account the discrete energy levels of the nucleus, were required to fully account for the observed phenomena. Fermi's work directly influenced numerous scientists and research groups around the world. Lise Meitner and Otto Robert Frisch, who provided the first theoretical explanation of nuclear fission, explicitly acknowledged the importance of Fermi's slow neutron experiments in their groundbreaking paper. Leo Szilard, who conceived the idea of a nuclear chain reaction, drew heavily upon Fermi's findings to develop his initial reactor designs. In essence, Fermi's slow neutrons acted as a catalyzing agent for various subsequent discoveries. The impact of Fermi's discovery extends far beyond its immediate applications in nuclear physics. His approach to scientific research, characterized by a combination of theoretical insight, experimental rigor, and a willingness to challenge prevailing assumptions, continues to inspire scientists to this day. The legacy of Fermi's work can be seen in the countless scientific endeavors that have built upon his foundation, from the development of nuclear medicine to the exploration of the universe. Enrico Fermi's 1934 discovery of slow neutrons stands as a monument to scientific ingenuity and a testament to the power of combining theoretical understanding with meticulous experimentation. It represents more than merely a single finding. It marks a paradigm shift in nuclear physics, opening up new avenues of research, revolutionizing our understanding of the atomic nucleus, and ultimately paving the way for the nuclear age. Fermi's work serves as a timeless reminder of the profound impact that scientific discoveries can have on society, transforming our world in ways that were unimaginable at the time of their inception. The story of slow neutrons echoes through the corridors of science, a quiet yet powerful testament to the transformative potential nestled within patient inquiry and a refusal to overlook the unexpected.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.